Alright, welcome everybody to week 9, day 1. Last time we talked about reading from a file. Today we're going to talk about writing to a file. And then we're going to talk about error messages in C++ and why they're terrible and why you can't fix it. And then we'll go into recursion as well. So, .cc. Wow, the font's small. Settings, appearance. There we go. Just make sure I'm not. Yeah, okay. That's what we're going to cover today. So, from the top, let's talk about IOStream, fstream, all this good stuff. So to review last time, if you want to read from a file, it's just like reading from CN, except it looks like this. ifstream ends reading from a file called min_corelli.txt. min_corelli.txt cat. Just copy that. Spelled it properly. Maybe I did, maybe I didn't. Okay. And first thing you should do when you open up a file is do something like this, like if.ends, cout, could not open the file, and quit. Or alternatively, you could just assert ends. That works as well. If you include the cassert header file. So, option 1, option 2. They do kind of the same thing. The first one is going to give you a more useful error message, maybe, to not open the file. The second one uses assert, and assert will tell you, it'll kill the program, and it will tell you which line of code it died on, which is sometimes also more useful. So, and there's a way of getting the current file, the current function, the current line number in C++ as well to make these errors more useful. Which one I would prefer? Probably this one. I would probably print out, could not open the file min_corelli.txt, and then it would let me know what was going on. Okay, so that's how you read from a file. So if an ifstream, an input file stream, is how you read from a file, what do you guys think you use to write to a file, to output to a file? Assert's more useful if you're opening a lot of files or in different locations. Yeah, it's less typing, and that's for sure. So if an ifstream is an input file stream, what do you guys think an output file stream is called? If you just had to wildly guess. If an ifstream is an input file stream, what do you think an output file stream is called? ofstream. Yes, very good, Marquez. So it is exactly the same as this one, except it's an ofstream. And so I'll use the first option for the first one for the input stream, and the second option for the second one. So you can have both options there. Now, what is this going to look like? G++ main.cc. So if we run it, everything worked fine. But let's say I don't have permissions on a file. And so there's a Unix utility called that comes with every version of Unix called Chmod. Change the mode of the file. The mode is the permissions of the file. And the syntax looks maybe a little bit weird, but basically it takes a 3 letters like this. Well, yeah, it could take more as well. But what it means is the user cannot read from min_corelli.txt. So I've just removed my permissions to be able to read min curly.txt. If I try opening it in Vim, I get a permission denied error. Okay, and if I run my program now says could not open the file. Even though the program like knows the file's there, it tries opening it and an error occurs. And so my code, anytime you work with files, you should always vet. You should always make sure that the file opening was successful, because you can have your permissions get broken. If you're on a file server, the file server could go down, you know, so you're trying to open a file on a file share and then it's just not there. You always want to, always, whenever you're working with a file, first thing you should do is just make sure the opening was successful. And if I want to grant myself read permissions back to it, it's u plus r, that means the user, me, plus grant read permission. Okay. And now if I run the program, it doesn't error. And then contrawise, if I say Chmod, I cannot write to Hazelton, Chmod, if I say I lose the write permission on Hazelton, then when I try running it, I get an assertion failed. So a.out, main.cc, line 16, inside of the function main, assertion outs failed. So it told me couldn't open, basically. Abort core dump. So it gives you a little more information about where the error occurred. It's a little less typing, but I don't use asserts in homework because the autograder compares the output of your program and the output of my program. So that's why we always use a die function, because the die function is just like bad input, die, you know, and then it'll match up. Whereas with this, if you use assertions in your homework, the line of code that you die on is probably going to be different from the line of code that I die on, and so they're not going to match up. So don't use assertions on your homework. But in real life, they're fairly common. It's the official way of doing a die function, but don't use it on homework. So much easier than trying to remember the numbers. Yeah, you can Chmod 777 Hazelton, and then it works fine. So you can see that Hazelton, there's all permissions. Everybody, even you guys, can now read and write and execute Hazelton. So. But if I run the program again, look, Hazelton exists now. I deleted the file, and then when I ran my program, because I'm creating a file for output, it actually creates it if it doesn't exist. If it already exists, like let me put Hazelton in here. Once upon a midnight dreary, while I pondered weak and weary over many a quaint and curious volume of forgotten lore, while I nodded, merely napping, suddenly there came a tapping, as of someone gently rapping at my chamber door. 'Tis some Yep. So okay. So if we look at the file Hazelton, I just put a bunch of text in there, right? First to the Raven, more or less. Probably made some mistakes, it's fine. So if I run this program, it's going to open hazelton.txt for writing. And when you open a file for writing in C++, by default, it deletes the existing file. It sets it to 0 file length. So all the permissions and all that stuff will stay the same, but the file will have anything in it purged. So all that effort I put into writing the Raven, if I now echo Hazelton, there's nothing in it. So be very careful to not open main.cc for writing. I've done that before, right? Like I'd have a program and I made like a word count program that would count how many times some word would appear. And I picked main.cc as the output file. And it, of course, overwrote my entire homework. And I had this moment of like, you know, just finish your homework, assignment. You're just like, I'm just gonna try, running this on this thing and running it on this thing. I'm like, oh, what would happen if I run it on main? Yeah, that was a sad day for humanity. C++ ate my homework quite literally. Yeah, fortunately I recreated that one fairly quickly, but that is not the only time I accidentally overwrote my homework. Tar, which is used to tape archive. It's like zip, kind of. You can zip up a folder. The first parameter, like a lot of people do this. Like, I'm gonna zip up all the .cc files. No, don't do that. Don't do that. Because the first parameter is the output file. So, sorry, CVF. So all of these things just got added to Bob. Tar, TVF, Bob.tar. So all these things just got added to Bob. If you forget this and just type this, the output archive is the first .cc file in your directory. So guess what? You thought you had a .cc file that had your homework in it. Not anymore. Not anymore. It's now a zip file, and or something like a zip file. So yeah, that's a true story right there. I did that once as well. Never again. Never a second time. You learn those lessons real fast. Okay. Is there a way to undo it? Nope. Nope. If you delete a file, like Bob ain't coming back. So, yeah. Don't make mistakes. If you really want to, you can use WinSCP to connect to the server and copy files over. It's probably a good idea to back up your directories every so often anyway. Yep, write the homework again. My friends are like, hey, we're going to a party. You want to come? Yeah, I do, but I can't. I have to do the homework. I thought you finished it. I did, yeah. When I went to submit it, I erased it. It was done. Yeah. Yeah, so this is why you use GitHub. Yeah, for sure. Yeah, version control is the thing for that reason. Damn, look at all these files I have in here. Maybe I should zip it up. Okay, so coming back in here, so what this does here is it creates a file named hazelton.txt and erases any existing file. It's called truncating. It sets it to length 0. There is a way of opening it in append mode, so it adds to the end of the file, but that's not as commonly used. Is there something like terminal that has easy undo? Yeah, you want to use source control. And so that's a really, really huge thing in the computer science world, which is version control, source control, where every time you make a change, you save it, and you have a versioning system, and the versioning system has every change you've made to the file ever. And if you ever screw up badly, you can undo and rewind back in time and then go forward again and stuff like that. It's a thing. Git is probably the most famous one right now. Okay, so now let's talk about what we can do with this. So Mincrel is full of doubles. Hazelton is full of nothing but hot air. Sorry, Hazelton. So a lot of computer science professors like to think of a program as a data transformation process. So I kind of disagree, because I write a lot of video games and things like that. But a lot of professors say there's 3 steps to most programs. The first step is gathering data. So you pull data in, either from the keyboard or from a file or from a network or from a database. Or a sensor, maybe. Then you transform the data. You do some sort of analysis on it. You've pulled in rainfall data. We did that on Friday. You're going to clean the data, throw away all the bad data, then do averages and means and medians and all this other stuff. And then at the end, you output. So step 1, gather data. Step 2, transform the data. Step 3, output the results. And the output could go to the screen, it could go to a file, it could go to a database, it could go to a network, or it could go to like an actuator, like turn a fan on or something. So inputs, transformation, outputs. I don't follow this model in most of my software because, like I say, I write games which have a loop that just sit there and spin over and over again and don't really transform data per se, you know. But this model that I'm about to show you is fairly common in computer science, so it's worth learning. So phase 1, input. So what we're going to do is we're going to load from a file into a vector. So min curly is full of doubles, full of rainfall data. So I'm going to make a vector of doubles, name vec, and I'm going to say while true. And I'm going to read from min_curly.txt until I hit the end of file. Oh, by the way, the quiz vanished off Canvas. I don't know what happened to it. So I put up the quiz for Friday up again, and it's going to be due on Wednesday. So there's going to be 2 quizzes due on Wednesday. There's going to be one for today and one for last Friday. Okay, so we're going to open this file. We're going to read data from it, and the data that we read is going to go into the vector. So let's make a thing, double temp. And we're going to read from the file into temp. And this is exactly the same as cn, except instead of cn, we're using ends. Ends is my generic name for an input stream, and outs is my generic name for an output stream. It's like vec. It's like if I got nothing better, that's the name I'm using. So we're going to read from the file into the temporary variable, and then we need to see if an error occurred. So if an error occurred, either what we read wasn't a double or we went off the edge of the file. There's another way we could do that, which is say if ends.eof. So did we hit the end of file? It's another way of doing it. Not ends is did an error occur, which is not exactly the same thing, right? Because if you try reading a squirrel into a double, an error occurs. So you can split those off into 2 different things. Like you can have your code for an EOF break, and then your code for an error after it, check for errors in the input file and stuff like that. Either way. So if an error occurred, then we simply break. We're done with the loop. If not, then we add vector.push back temp. If not, then we add the value that we read to the end of the vector. So this is the standard. I'll do option 1 here. Option 1, use fstreams to read values from a file into a vector. Right? Does this make sense to you all? This is what we covered on Friday. So we're going to loop over a file, reading, putting the values into a vector. Yeah. You guys remember that from Friday? Yeah, an RM undo is a fairly common thing that people will do. Okay. So let me show you guys how I would do this with readlib. So let me show you how compact this is if you use my read library. So while ends is valid, I'm gonna have to comment this out. Okay. So while ends is valid, vector.push back read a double from ends. Okay. So in one line of code, this will read all of the doubles out of a file and put them all into the vector. Trouble is, the very last read you do is an error. And so you'll end up with an extra 0 at the end of it. And I've thought about different ways of fixing that. I might just write I don't know. I might make like a single line command that will just have a vector and a file and just read all the values into the vector. I don't know. Maybe. I don't know. But version 2.0. Yeah. So, but what you're going to do is if you read anything, you're going to end up with an extra 0 at the end, because the last read you do fails because you go off the edge of the world, and it'll put a 0 at the end of the vector. So we have to say if vector.size, if we read anything at all, then delete the last element in the vector. So 2 lines of code instead of 6, 7. It's still more compact, and this thing here kind of annoys me, so I've been thinking about ways of making it even easier for you guys. But that's an even simpler way of reading. So that's phase 1, read from a file. And then phase 2, transform the data. First thing I'm going to do, as always, is I'm going to see it out, right? So for every double in the vector, echo it to the screen. So let's just make sure that everything's working. There's the data, mid-Corelli 4.4, 5.5, 4.4, 5.5. Okay, so we are reading the file properly. And the last element is -99. Last element in Corelli is 99. Yeah. Cool. So now let's double all the values. Okay. Read library update. I think so. So you could read strings from a file into a vector. Yeah. Yeah. If this was strings instead of doubles, you could read every word in a file into a vector, and it would work very cleanly. You know, just this is the only kind of annoyance in it. Yeah. Or I mean, we could always just put into a regular loop like this too. These 2 lines would compact down into a read statement. Yeah. No. Okay. So let's transform the data. Let's double all the values in min-Corelli. Okay. So for every double by reference x in vec, x is equal to x times 2. So for every element in the vector, we are going to double it. What do you think? You guys understand that? For every element, for each element x in the vector, set that value equal to twice its current value. Make sense? So we've read a bunch of values from a file, we're doubling them all, and then we're going to write them into Hazelton. That's it for phase 2. We're done. It's 1 line of code. Okay, all right. Seems like you guys got this pretty well. All right, so phase 3, write the data. So you're going to read the data, transform the data, then write the data. So what we're going to do is we are going to dump all of this data into Hazelton. So Hazelton is linked to that variable there, outs. And we're done. What? Yep. That's it. So writing to a file is pretty easy. The only difference between this and couting the data to the screen is we just changed the cout from cout to outs. Outs is the name of the variable we created that is connected to hazelton.txt. That's it. If you knew how to print a vector to the screen, you know how to write a vector to a file. It's exact same code. You just choose whether it goes to the console out or to the file that you've created. Just choose where the data goes. If hazelton.txt already has values, will they be appended to the end? No. it will erase any existing data in Hazelton. It truncates the file. When you open a file here, any data in Hazelton goes away. Down here, yeah, it'll append to the end. It's when you open the file that it truncates, and it goes away. So there's the program. Wait, it didn't print anything to the screen. I know. There's no cout statements. There's no cin statements. The program runs. It reads from a file, doubles all the values, and writes to Hazelton. So if we cat and Corelli, there's that. If we cat Hazelton, there's all the values doubled. So 4.4 turns into 8.8, 5.5 turns into 11, 0 turns into 0, 100 turns into 200, negative 99 turns into negative 198. That's it. And a lot of programs actually look like this. You run it, and then they pause for a second as they churn through hundreds of thousands of things, and then they terminate. And they don't even print anything to the screen. It's actually fairly common. Like if you have a utility or something, you know, let's say you have, let's say you're running a website, and the website has logs, HTTP logs, and once an hour you have a program set to automatically run once an hour that will find the top 100 IP addresses that are connecting to your site, and then write them to a file, and the file is going to be in HTML format, and you write it to your public HTML directory. And so what happens is that just, you know, your system administrator or whatever, you know, can have a tab open on their browser, and every hour it refreshes and shows them the people that are hammering the site the most. And then they get to decide, do I ban this IP address? Do I allow it? You know, that kind of stuff is very common in business. Like, you just write these little tools. It doesn't need to echo anything to the screen. Why? Because there's no screen. It's being run inside of like a timer utility. There's something called cron in Unix. And cron, you can say, run this program once an hour. And you don't see out anything. Why would you see out anything? It's the cron daemon that's running it. It doesn't care what your output is. In fact, a lot of times if you output things, it mails you the console. Hey, by the way, I ran this program and this is what it outputted. You're like, no, don't output anything, because then I get an email every time. I don't want an email every hour. No, turn that off. Print nothing, please. You know, and so every hour it'll run, and your website just automatically updates every hour. You know, you can see who the current consumers of your bandwidth are and make decisions about it. Do I ban them or allow them? How do you write something like the read library? That's a big topic, and not one we have room for today. But ask me in the future. We'll talk about header files at some point. Okay, so yeah, so the program opens, transforms, writes, and prints nothing to the screen. Pretty normal. So that was our first learning point for today. So the first learning point for today is how to write to a file. Okay. Second learning point, C++ error messages and why they suck. Okay, so this was asked in the previous class, and if I go into something in a previous class, I try to make sure I say it in the later class as well. So he was saying I was getting too many error messages, and I couldn't even scroll up high enough to see what was going on. And that'll happen. Why? Because C++ error messages suck. They have sucked since the 80s. It is the primary complaint a lot of people make about C++, is that they're just no good. They've gotten better. They've gotten actually a lot better, significantly since 2016. Like, they've actually gotten noticeably better, but they still suck. They're hands down one of the worst languages for error messages, with the possible exception of PHP, where, Mr. Bell, have you ever had code that have you ever had PHP have an error? PHP bad with errors. PHP is bad with a lot of things, yeah. So yeah, so let's make a variable called x. I think we used x down below. Let's make a variable called a that's equal to 5 and a double called b that's equal to negative 1.1. And let's try swapping the values of a and b. Doesn't work. You think it should work, right? It should truncate negative 1.1 to negative 1, and it should, like a lot of people will try this. Like, you should be able to switch the values, right? Because you can set them equal to each other. But swap doesn't work. Swap has to only take two things of the same type. So if we look at the claim D error message here, we say it's pretty understandable. No matching function call. Okay. It doesn't explain why. Like, it should say you can't swap an int and a double. Like, that would be a reasonable error message. So let's run this in G++ and see what we get. G++ main.cc. Scroll up, 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 scroll up. Oh, there we are. Hello. So the actual error message is always at the top. Okay, and so what you want to do when you get an explosive error message like that is don't pay attention to the bottom stuff. The bottom stuff is almost always useless. And in fact, all of these notes, anytime you see a note, you can probably ignore it because it is just the compiler telling you things that it tried that didn't work. And the things that it tries are stupid. Like, so dumb that it's actually making me dumber looking at these notes than if I had not seen these notes. And there's no way, as far as I know, of turning them off. There's a way of sort of mitigating them, but you can't turn them off. Like, I could filter them out, maybe, using grep or something like that. But, like, compilers which have flags for everything, you can turn on and off every warning message possible in human existence, doesn't allow you to turn this off. Why? Because we went to the effort of making these candidates for swapping. You are going to read them. That's what they're telling you. We went to all this effort. You are going to read them. But what do they mean? Let's talk about it. So what we see down here is that, so the root problem is that you can't switch an integer and a double. Okay? Swap takes two things of the same type. That's the problem. What it's trying to do, though, it's trying to convert... at this point, I don't even know what's happening. This is something called a hash table, which you'll learn about in CSI 41, which is a way of very quickly storing millions and millions of numbers, possibly. And it's trying to say, all right, I tried to see if I could switch a hash table with an integer. And you know what? You couldn't. Couldn't do it. Right here. Template, argument, deduction, substitution failed. I tried this. It didn't work. So why are you telling me? Nobody in their mind would think about swapping a hash table and an int. Like, if an int and a double, yeah, maybe. Like, maybe you might try that once. You know, switching a hash table and an integer. Who in their right mind would even think that that was the thing that you wanted it to do when you were trying to switch an integer and a double? Nobody in their right mind would ever consider that what I really meant was a hash table and an integer switching. And the fact that that didn't work should surprise nobody, and I am now stupider for having read that. And so it tried that. It tried switching a hash table and an integer, and it didn't work. Then it tried switching another kind of hash table, and that didn't work either. And if we come up here, it tried switching between a function and an integer. Guess what? Functions and integers, they can't be switched either. Who knew that? I did. Everybody with brains knew that you can't swap an integer and a function because it makes literally no sense. And it's telling you all of these things that it was trying that you can't do. And if you want to know how many error messages you get, there is the pipe character. And the pipe character with the ampersand means pipe even the error messages, which is what we care about because we're getting error messages. We can pipe it through a program called word count, and word count will tell you how many lines, words, and characters there are. Or you can do word count -L. And we got 243 lines of error messages. And this is the kind of thing that terrifies first semester students when they see it for the first time. Because they're like, I must have done something really wrong. I must have done something really wrong to have gone 243 lines of error messages. My code must be irredeemably broken? And the answer is no, it's not. It's the compiler's fault. The compilers are dumb when it comes to error messages, especially whenever you see this thing here, template substitution errors. Template substitution errors for whatever, why, I don't know, why. They don't let you turn them off. They will spam. They're not even error messages. They're just telling you things that the compiler thought you might want to know about and you didn't even consider, but they're telling you, we tried it and it didn't work, and you can't turn it off. There's ways of mitigating it, but there's no flag to just not print those, which is one of the single greatest issues that I have with modern compilers. You can scroll up. These are all template argument substitution factors. Yeah, all it needed to print was this. That's all I needed to do. That's the only thing you need to print. The top error message. Everything else is idiotic and a waste of time. So what you want to do if you have a situation like that is you can pipe the results through head. Head cuts off just the top 10 lines. So all those extra lines of error messages go away, and you just get to see the top 10 lines. You can show just the top 3 lines if you want, but head's fine. And that chops off everything down below, and then you can see where your error is. Okay, error no matching function call to switch it into a double. And that'll hopefully clue you in as to what the problem is. It's still not super useful, but you know, that's at least the problem. Everything else was just a waste of space. It was 241 lines of wasted space. And it just pisses me off to no end that compilers like, here you go. No, you have to have it. I don't want it. You have to have it. Can you give me a flag to turn it off? No, you have to have it. What use is it? There's no use to it, but you have to have it. It's like baffling why that is a design decision that somebody made. Is there a language with good error messages? Java, maybe. C++ is worse than most, though. I will say that absolutely. It's absolutely worse than most. Okay. Sad head loses colors. Yeah, pretty much every time you pipe something, it loses colors. Another very common thing is to pipe the results through less or more, but more is less. They basically work the same way. Less is a little bit better than more. And then you can scroll up and down through the error messages if you want to do it. So more and less are both things called paginators. They take a ton of text and they display it one page at a time. So if I were to pipe the results into more, I can hit space and it goes through one page of text at a time. More doesn't allow you to scroll back up though, so less is a little bit better than more. So I can still hit space, but then I can scroll up, and you can hit Control G also in less, and it shows you how far you are and stuff like that. So yeah, this is a very common thing. You should write this down in your brain. Anytime you get a lot of error messages, do that, and then just look at the top line. All of them lose colors, but such is life. Okay, so that was the second learning point. Use this to show me and Carly made a meme in the previous class, which is fantastic, and absolutely spot on too. It's from Rick and Morty, obviously. C++ compiler, what is my purpose? To confuse C++ programmers. Yeah. Yeah, but I don't want to crap on, you know, compiler authors too much, because they've actually done a really, really fantastic job at improving the quality of error messages in the past 5 years. Like, it's actually been an area where huge strides have actually been made. You can actually look at the difference in error messages over time, and they're getting better. They're actually a lot more understandable. They have colors now. They'll highlight exactly where in the line you screwed up, things like that. Okay. All right, so final topic for today is we're going to start talking about recursion. So recursion is when a function calls itself. Okay. And show old errors and see what idiotic is learning. Yeah, we're running out of time. If you want to paste some, Mr. Bell, they're definitely better now. Okay, so recursion is when a function calls itself. So for example, I can make a function that I don't know. So foo is a function that calls foo. And that's a function that calls foo. And that's a function that calls foo. And that's a function that calls foo. So what do you think is going to happen when you have an infinite loop like this? Generate the longest error message in C++. Yeah. 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 Okay. What do you think is going to happen? You get stuck. Yeah, it's an infinite loop. But does it run forever or does it crash? Well, let's find out. Crash. So every time a function calls itself, it allocates a little bit of memory. And the stack space has a limited amount of memory. And so every time a function calls itself, it starts running out of stack, and eventually it segfaults and dies. So recursion is dangerous, right? Because if you run out of stack space, it kills your program, and it's unrecoverable. A lot of errors, like a lot of out-of-memory errors, you can actually recover from. Out of stack space errors, you can't recover from, because any code to recover from the stack space running out would have to go onto the stack, and it can't, so it just dies. So this is bad. Okay. So let's make a function for the Fibonacci sequence. Fibonacci sequence. And it's going to take the index in the sequence. Do you guys remember the Fibonacci sequence? We did this a week or so ago. Fibonacci sequence is 1, 1, 2, 3, 5, 8, 13, 21, 34. Right? You guys all remember that? Recursion is used when a problem is self-similar. Often, you don't have to use it. So, the Fibonacci sequence is defined recursively. The Fibonacci, the 10th Fibonacci number is the sum of the 8th Fibonacci number and the 9th Fibonacci number, right? It's recursively defined in terms of itself. It exhibits the self-similarity principle, where smaller versions of the problem, like Fibonacci 5, is also the sum of 3 and 4, and 10 is the sum of 8 and 9, and 100 is the sum of 98 and 99, right? At every level, the program resembles itself at smaller and smaller levels until you get down to the very bottom here. Okay, so and then that's like the starting point. So anytime you have a problem that's self-similar that way, like in CSI 41, you're going to learn about trees. Trees in computer science don't refer to marijuana, although they can, depending on who you talk to. A tree in computer science is a thing that looks kind of like this. The root of a tree is in the air, and the leaves of a tree are on the ground for some reason. That's upside down. Yeah, the root of the tree is in the sky, and the leaves are on the bottom. And so the way that the most common tree works is called a binary search tree. The rule for a binary search tree is that everybody to the left is smaller than me, and everybody to the right is bigger than me. That's actually wrong. You can't have two 49s. So like here, everybody's smaller. Interesting. They have duplicates all over the place. I don't know what's going on here. All right, let's try this one. Okay, so everybody to the left is smaller than me. Everybody to the right is bigger than me. And that is recursively true. So down here, everybody's smaller than me to the left. Everyone's bigger than me to the right. Down here, everyone's smaller than me to the left. Everyone's bigger than me to the right. So it's a recursive property that no matter where you are, the property holds. You know, everybody to the left is smaller than 20, right? And so because of that, traversing a binary tree like this is very easy. You can write recursive algorithms. Like if you want to sum up all of the numbers in this tree, what you do is you say sum up all of the people in the left subtree, then add my value, and then sum up all the people in the right subtree. And that's it. It's like a line of code, maybe 2 lines of code, because you're going to run off the edge, right? And so you'd say if I'm null, if I've run off the edge, return 0. Otherwise, yeah, that's it. It's like 2 lines of code, and it's going to go like down, down, down here, and then up, then down, then up, then right, then down, then up, then right, then up, then up, then up, then right, then left. Like the actual behavior of it's actually quite complicated, but the code is very simple to write. And so that's why when you have a self-similar problem like that, a lot of times we'll use the recursive, we'll use like a recursive function or yeah, we'll just leave it at that. So to define Fibonacci, we can simply return Fibonacci index -1 plus Fibonacci index -2. Right? Is this going to work? What do you guys think? What do you think? Is this code going to work right, or is it going to run forever? Trees are like a function. They're a data structure. So a data structure, the only data structure you know right now are vectors. A data structure is something that can hold thousands or millions of variables. They hold lots of variables. And so a tree is a way of holding the variables in a way that it's ordered with smaller things to the left. A binary search tree is ordered smaller things to the left and bigger things to the right. And that makes finding things very easy, right? It's like a phone book, A phone book's easy to find names in a phone book because it's sorted, all right? So you can open it up halfway and, you can find names in a phone book very quickly because it's sorted. And a binary tree is always sorted like that. So is this code going to run forever, or is it going to stop? Well, you'll eventually go over 2.1 billion. Overflowing doesn't stop, right? Doesn't quit your program when you overflow. Forever or stop? Well, technically you're both right. Yeah, it's an infinite loop, but it's an infinite loop that's going to segfault. Because it's going to keep calling itself, right? So the Fibonacci of 5 is going to call the Fibonacci of 4, the Fibonacci of 4 is going to call the Fibonacci of 3, the Fibonacci of 3 is going to call the Fibonacci of 2, which is going to call the Fibonacci of 1, which is going to call the Fibonacci of 0, which is going to call the Fibonacci of -1, which is going to call the Fibonacci of -2, and it's just going to run infinitely until it runs out of stack space and crashes. So we need to go over a very important point here, which is like a lot of people don't use recursion because it can run out of stack space and crash. Okay. It's like Microsoft, if you write a recursive algorithm, you have to prove your algorithm won't crash. And so that can be tough to do. So a lot of times people at Microsoft just don't write recursive algorithms because it's just a pain to prove that the thing is never going to run long enough to run out of stack space and crash. So every successful recursive algorithm needs 2 things. First, a base condition that ends the infinite loop. Second, an inductive step that moves you towards the finish line. Okay, so the base condition's like the end zone in a football game, right? When a person has the football, they run towards the end zone, and when they hit the end zone, they're done. Okay, that's what we're lacking here. We're lacking any ability to finish. Every time we call Fibonacci, it just calls Fibonacci, which calls Fibonacci, which calls Fibonacci, which calls Fibonacci, which calls Fibonacci. What we need is a end zone stop, and that is pretty simple. If the index is less than 2, return 1. So now it'll stop. So once we get to below 2, it ends. Okay, and now we've got a working program. If we do this, then the Fibonacci 5, 0, 1, 2, 3, 4, 5 is in fact 8. Okay, and so you need to have a finish line, and then you always have to be moving towards the finish line. And so, like for example, if I did this, if I say return the Fibonacci of index +1, now it's infinite again, right? Because the finish line's at 0, and we're running away from 0. Does that make sense? So what's the Fibonacci of 3? Well, it's the Fibonacci of 4. Well, it's the Fibonacci of 4. It's the Fibonacci of 5. What's the Fibonacci of 5? Fibonacci of 6. And even though we're ending when the index is less than 2, we're running away from it. Like Forrest Gump, right? Forrest Gump would cross over the finish line and just keep running, right? So you have to have a finish line, and you have to stop, and you have to move towards it, you know, every time, if that makes sense. So if we run this code, it'll segfault. Okay. So you must always, to have a good recursive program, you must have a well-defined finish line, and you must always be attracted, you must always be moving towards the finish line. So if we pass in Fibonacci of 10, we're going to go to Fibonacci of 9, to Fibonacci of 8, moving towards the finish line, and then it terminates. That's the key to a good recursive algorithm. So one interesting thing about recursive algorithms is that they're actually substitutes for loops. And one person I met up in Seattle at CPPCon, they actually learned recursion prior to learning a loop, which is weird because recursion hurts students' brains. The only way you can understand recursion is to understand recursion, and in order to understand that, you have to understand recursion. In order to understand that, you have to understand recursion. It's a hard thing to wrap your mind around. So I thought it was kind of weird, but they're like, yeah, look, if you can do loops using recursion, then you don't need to learn loops. Like, we didn't learn for loops until like way later in our career. And I was like, all right, it's kind of weird, but I guess it's true. All you need to learn is functions in that case. So let me show you how you can replace a loop with a recursive call, okay? And let's see here, let's make a function called vector print. Vector print is going to take a vector of doubles named vec, and it's going to take in an index of which spawn in the vector to print. And so down here, rather than, yeah, let's just do this. Let's do vector print vec starting at 0. So this will print the vector to cout. Okay, so we're going to make a function that takes a vector of doubles, and it's going to start printing it starting at index 0, and it's going to print to the end. Okay, so normally we do this with like a range-based for loop, like this, but we're going to do it with recursion instead. And question for you guys, should we be doing, this is call by value, should we be passing the vector as call by value, call by reference, or call by const reference? Those are the three options. We're passing in a vector. The vector could have 1,000, 1,000,000 doubles in it. How should I pass it to this function? It's call by value right now. Call by value means duplicate the vector every time. So if you pass in 1,000 vectors, it'll duplicate all 1,000. And then when it recursively calls itself, it'll duplicate itself another time. Then it'll duplicate itself another time, another time. Call by reference. Yeah, that's better. But should a print function change the vector? Like if I'm passing my vector to a function called print the vector, would I expect it to come back modified? No. Yeah. So this should be const vector, a const reference. And that's my go-to. Like usually when I pass a vector to a function, I'm going to pass it const reference unless I need to otherwise. That's like my go-to. Okay. So we're going to print this vector starting at index. Okay, so what we're going to do is say if index is less than vector.size. So we are doing a little bounds checking here. So if we're being passed a vector of size 10 and I'm being asked to print out vector element 20, that's out of bounds. So we're not going to do anything in that case. So in the case where we're out of bounds, I don't know, do nothing. Just return. Okay, so, but if we are within bounds, so if we have a vector of size 10 and we're being asked to print element 2, let's just print it. Okay. And I'm using square brackets here because I just bounds checked it. Like this is a pretty direct bounds checking here. So I feel safe using square brackets there. For you guys, use .at anyway. So Yep. So if we're printing out element 0, then we print it, and then we are going to do a recursive call. So we're going to now call vector print again, vector print. We're going to pass in the vector again, and we're going to pass in index plus 1. So we are going to recursively call ourselves, passing in the same vector by reference, so it doesn't make a copy. And instead of 0, it's now going to be 1. And then it's going to print vector.at1. And then it's going to recursively call itself again and do vector.at2, vector.at3, vector.at4, 5, 6, 7, 8, 9. And then when it gets to vector.at10, 10 would then be greater than our size of 10. It does nothing, it just returns, and then that returns, and then that returns, and that returns. And in fact, we don't even need to do this. That's good enough. Because if you get to the end, of a function, it just returns. Right? You don't need a return statement there. So there you go. So this is, notice how there's no loop. There's no for loop, there's no while loop, there's no do while loop, there's no range-based for loop. There is no loop anywhere in here. We are using a recursive function call to iterate across a vector. Right? So the first time we call it, we pass in vector, and we pass an index of 0, then it calls itself, passing an index of 1, and it calls itself again, passing an index of 2, and so it's a replacement for loops. With the small downside that if the vector is too big, the thing crashes. Right? If you're trying to print out 1,000 elements or more, good luck. It might run out of stack space and just crash. So I would not use this. Okay, but it works. See, it just printed the vector out. It's fine. It's fine right up until it's not. Right. So this is a recursive. Okay. It really depends also on the optimizer and things like that, but I wouldn't write a function like that. I would just, rather than, all that, I would do that. It's less typing, right? But the point of this is that loops and recursion are kind of equivalent concepts. They're sort of interchangeable at a certain level of thought. Okay. Any questions about this? Do you guys understand what this is doing? Keeps calling itself over and over again, just passing in the next element, and then once it gets to the end of the vector, it stops. You guys cool? Recursion is hard to wrap your mind around, so it's okay if you don't. By the way, the running time of this is horrible. For every function call, it calls itself twice. So that's exponential running time. It's a really, really bad algorithm, by the way. It's very useful for demonstrating how recursion works, but you don't want a function that doubles its running time every time the number goes up by 1. Hurts your brain. Recursion hurts your brain. Yeah, it's normal. It's part of the growth process of computer science. Computer science, your brain will get stretched over and over again. So. All right, that's it for today. And that function is order. No. It is not order n squared. No. This is something along the lines of order 2 to the n. So as you ask it to compute more Fibonacci numbers, the running time doubles. Right? If you are at Fibonacci 100 and you're computing Fibonacci 101, you're going to do 2 calls, one to Fibonacci 100, one to Fibonacci 99. So 102, it's going to call 101 and 100, and 101 is going to call 199, and 100 is going to call 99 and 98, and 99 is going to call 98 and 97, and it doubles in running time every additional Fibonacci number you try to compute. Is there a way to see the running time? Yeah, sure. Let's see. Caps lock that. Okay. And so we'll ask which index, and then we will see out Fibonacci passing in none. So the smaller one's pretty fast, right? See it start lagging there? Okay, so if we time a.out, oops. Yep. So it took 4 seconds. Six seconds. Yeah, because it's not exactly double, because one of them is 2 down instead of 1 down. But yeah, it is an exponential growth. So if we go up to 46. Yeah, 46 is not a large number in computer science, you know what I mean? Like, it went from 6 seconds to 10 seconds to compute one more number. And all you have to do, right, is like we did this before. You just have the last 2 numbers in a vector and you add them up and get the new one. Like, there's absolutely no reason for it to take this long. It's just a really, really, really bad algorithm that nonetheless you will see all over the place because it's useful for demonstrating recursion, right? Like, this teaches you how recursion works. You can have one function call itself, self-similarity principle, all that stuff. Don't use this in practice because it is utter garbage. Absolute and complete painful garbage. So, all right, so that's it. I'll see you guys on Wednesday. And remember, there will be 2 quizzes due on Wednesday, one for today and one for Friday, because that quiz vanished into the ether somehow. So, see you guys then. Peace out.